हेलो बच्चों, कैसे हैं आप सब लोग। वंस अगेन वेलकम टू आवर चैनल बीट द नीट। और देखिए मैं आप लोगों के लिए क्या लेकर के आई हूँ, फिजिक्स की ऑडियो बुक। क्योंकि मेरे सारे वीडियोस पे जो भी मैंने रिसेंटली वीडियोस अपलोड कर रही हूँ उन पे सब पे कमेंट आ रहा है कि मैम आप ये फिजिक्स वाली ऑडियो बुक्स कंप्लीट कर दीजिए। भाई यूट्यूब में कहीं पर भी अवेलेबल नहीं है। और आप सभी को पता है कि मेरे चैनल पे जितना भी कंटेंट अवेलेबल है वो सारा फ्री ऑफ कॉस्ट आप एक्सेस कर सकते हैं। सारा टेलीग्राम चैनल पे भी आपको सारा कंटेंट आपको आराम से अवेलेबल हो सकता है। तो भाई जो बच्चे नए हैं, आपने अभी तक चैनल को नहीं सब्सक्राइब किया है तो कर लीजिए बेटा, क्योंकि आप लोगों की नीट प्रिपरेशन में, आपकी बोर्ड की प्रिपरेशन में ये चैनल बहुत हेल्प करने वाला है। और आप देख सकते हो कि फिजिक्स की ऑडियो बुक कहीं पर भी नहीं मिलती है, सिर्फ यहीं पर आपको मिलेंगी, जो आप इजीली सुन करके जो थ्योरी वाले चैप्टर्स हैं उनको रिवाइज कर सकते हैं। बहुत सारे बच्चों की रिक्वेस्ट आ रही थी कि मैम आप फिजिक्स वाली ऑडियो बुक्स, क्योंकि मुझे ना उस पर रिस्पॉन्स उतना अच्छा आप लोगों ने नहीं दिया जितना अच्छा आपने मुझे रिस्पॉन्स मेरी बायो वाली ऑडियो बुक्स पे दिया। आउटस्टैंडिंग रिस्पॉन्स इट इज़। एंड केमिस्ट्री की भी और दिया, एंड बायोलॉजी की, इवन जो हिंदी की ऑडियो बुक मैंने बनाई उस पर भी आपका बहुत अच्छा रिस्पॉन्स आया। बट आपने पता नहीं क्यों फिजिक्स वाले में शायद आप लोग कम सुनते हैं, तो मुझे लगा कि शायद इतनी ज़रूरत आपको नहीं है, तो इसलिए मैंने उस प्रोजेक्ट को थोड़े दिन के लिए होल्ड करा। बट अभी मेरे पास है बच्चों के वापस से कमेंट आ रहे हैं, बाकी सारे वीडियोस के ऊपर भी वही कमेंट आ रहे हैं कि मैम आप फिजिक्स वाली ऑडियो बुक्स कंप्लीट कर दीजिए। तो इसीलिए मैंने सोचा कि भाई जब बच्चों को ज़रूरत है तो मैं ज़रूर बनाऊंगी। लेकिन बच्चों आप लोगों से भी मैं एक्सपेक्ट करती हूँ कि आप भी इसको ज़रूर अपने दोस्तों के साथ में शेयर करेंगे, ताकि इनको भी उतना ही प्यार मिल सके जितना मेरी बाकी की वीडियोस में आप लोग देते हैं। तो आज मैं आप लोगों के साथ में करने वाली हूँ चैप्टर 12 एटम्स, क्लास 12 का है। एंड ये थ्योरेटिकल चैप्टर है, इसलिए इसकी ऑडियो बुक अवेलेबल नहीं थी, तो मैंने सोचा इसकी पहले मैं बना देती हूँ। थ्योरी वाले चैप्टर्स को हम पहले कंप्लीट करते हैं। साथ ही साथ में मैंने न्यू एनसीईआरटी की ऑडियो बुक्स भी स्टार्ट कर दी हैं, ताकि जो बोर्ड में बच्चे हैं उनको भी रिवीजन करने में ईजी हो, तो वो बच्चे भी जा करके देख सकते हैं। जो बच्चे अभी तक टेलीग्राम चैनल नहीं ज्वाइन किया है तो भाई ज्वाइन कर लीजिए। जब मैं आप लोगों को सारी चीज़ें फ्री ऑफ कॉस्ट प्रोवाइड कर रही हूँ, कम्युनिटी में जाकर के आप क्वेश्चंस करिए। मैं डेली कम्युनिटी आप लोगों के लिए शेड्यूल करती हूँ, ताकि आप लोग को डेली क्वेश्चन प्रैक्टिस मिल सके। अब और इससे ज़्यादा आप लोग के लिए क्या किया जाए, आप लोग उसको सब्सक्राइब करेंगे, नोटिफिकेशन ऑन होगा तो आप लोगों को सारे अपडेट्स मिलेंगे। सारे आप लोगों के पास में एग्जाम के अपडेट, सारी चीज़ें मैं प्रोवाइड करने की कोशिश करती हूँ। तो आई होप कि आप लोगों की ये वीडियो ज़रूर हेल्प कर रहे होंगे। एंड आप लोग मुझे इसी तरह से कमेंट सेक्शन में बताते रहिए अपनी रिक्वायरमेंट्स कि मैम हमें इन चीज़ों की ज़रूरत है, अगर आप ये पहले बना दें तो इट्स बेस्ट। तो मैं उन टॉपिक्स पे वर्क करना स्टार्ट करूँगी पहले, क्योंकि हेल्प तो आपकी करनी है ना। तो इसलिए अगर आप बताएंगे तो ही मुझे पता चलेगा कि बेटा आपको इन चीज़ों की ज़रूरत है। अब आपने बताया कि मैम फिजिक्स ऑडियो बुक पहले चाहिए, तो इसीलिए मैंने इन्हें पहले स्टार्ट कर दिया। बाकी आप लोग जैसे जैसे बताते जाएंगे, चैप्टर्स आप पोस्ट करिए कि मैम मुझे इस चैप्टर की ऑडियो बुक चाहिए फिजिक्स में, तो मैं उन चैप्टर्स की ऑडियो बुक पहले बना दूंगी। क्योंकि जनरली बच्चे थोड़ा एनसीईआरटी कम ही प्रेफर करते हैं फिजिक्स के लिए। थ्योरेटिकल चैप्टर्स में क्वेश्चंस आते हैं थ्योरी वाले पोर्शन से, लेकिन जनरली बच्चे जो है कम प्रेफर करते हैं। तो इसीलिए मैंने इस प्रोजेक्ट को थोड़ा सा होल्ड कर दिया था। बट अब आपकी रिक्वेस्ट जैसे ही आई वैसे ही मैंने इसको स्टार्ट कर दिया। तो आपसे मेरी ये रिक्वेस्ट है कि आप लोग चैप्टर नेम मुझे सजेस्ट करें कमेंट में कि मैम इन चैप्टर्स की आप पहले प्रोवाइड कर दीजिए, तो मैं उनकी ऑडियो बुक्स आपके लिए फिजिक्स में पहले बना दूंगी। ओके। और आई होप कि आप लोग मेरे सारे वीडियोस देख रहे होंगे। 1 मिनट बायोलॉजी मेरे जो टीचिंग के स्टार्ट किए हैं, एंड जो न्यू एनसीईआरटी है, बहुत सारे वीडियोस चल रहे हैं, तो आप लोग आई होप कि उन सबको एंजॉय कर रहे होंगे। एंड मैं उतना ही प्यार इन ऑडियो बुक्स पे आपके एक्सपेक्ट कर रही हूँ जितना प्यार आप लोगों ने बायोलॉजी के लिए दिया। सो चलिए स्टार्ट करते हैं। बहुत सारी बातें कर ली हमने। चैप्टर 12 एटम्स, इंट्रोडक्शन 12.1 इंट्रोडक्शन। By the 19th century, enough evidence had accumulated in favor of atomic hypothesis of matter. In 1897, the experiments on electric discharge through gases carried out by English physicist J.J. Thomson, 1856 to 1940, revealed that atoms of different elements contain negatively charged constituents, electrons, that are identical for all atoms. However, atoms on whole are electrically neutral. Therefore, an atom must also contain some positive charge to neutralize the negative charge of the electrons. But what is the arrangement of the positive charge and the electrons inside the atom? In other words, what is the structure of an atom? The first model of atom was proposed by J.J. Thomson in 1898. According to this model, the positive charge of the atom is uniformly distributed throughout the volume of the atom, and the negatively charged electrons are embedded in it like seeds in a watermelon. This model was picturesquely called plum pudding model of the atom. However, subsequent studies on atoms as described in this chapter showed that the distribution of the electrons and the positive charges are very different from the proposed in this model. We know that condensed matter, solid and liquids, and dense gases at all temperatures emit electromagnetic radiation in which a continuous distribution of several wavelengths is present, though with different intensities. This radiation is considered to be due to oscillations of atom and molecules governed by the interaction of each atom or molecule with its neighbors. In contrast, light emitted from rare-field gases heated in a flame or excited electrically in a glow tube, such as the familiar neon sign or mercury vapor light, has only certain discrete wavelengths. The spectrum appears as a series of bright lines. In such gases, the average spacing between atoms is large. Hence, the radiation emitted can be considered due to individual atoms rather than because of interactions between atoms or molecules. In the early 19th century, it was also established that each element is associated with a characteristic spectrum of radiation. For example, hydrogen always gives a set of lines with fixed relative position between the lines. This fact suggested an intimate relationship between the internal structure of an atom and the spectrum of radiation emitted by it. In 1885, John Jacob Balmer (1825 to 1898) obtained a simple empirical formula which gave the wavelengths of a group of lines emitted by atomic hydrogen. Since hydrogen is simplest of the elements known, we shall consider its spectrum in details in this chapter. Ernest Rutherford, 1871 to 1937. A former research student of J.J. Thomson was engaged in experiments on alpha particles emitted by some radioactive elements. In 1906, he proposed a classic experiment of scattering of these alpha particles by atoms to investigate the atomic structure. This experiment was later performed around 1911 by Hans Rieger (1882 to 1945) and Ernest Marsden (1889 to 1970), who was a 20-year-old student and had not yet earned his bachelor's degree. The details are discussed in section 12.2. The explanation of the results led to the birth of Rutherford's planetary model of atom, also called the nuclear model of the atom. According to this, the entire positive charge and most of the mass of the atom is concentrated in a small volume called the nucleus, with electrons revolving around the nucleus just as planets revolve around the sun. Rutherford's nuclear model was a major step towards how we see the atom today. However, it could not explain why atoms emit light of only discrete wavelengths. How could an atom as simple as hydrogen, consisting of a single electron and a single proton, emit a complex spectrum of specific wavelengths? In the classical picture of an atom, the electron revolves round the nucleus much like the way a planet revolves round the sun. However, we shall see that there are some serious difficulties in accepting such model. So here is Ernest Rutherford, some information is also there. Ernest Rutherford, British physicist who did pioneering work on radioactive radiation. He discovered alpha rays and beta rays along with Frederick Soddy. He created the modern theory of radioactivity. He studied the emanation of thorium and discovered a new noble gas, an isotope of radon, now known as thoron. By scattering alpha rays from the metal foils, he discovered the atomic nucleus and proposed the planetary model of the atom. He also estimated the approximate size of the nucleus. 12.2 Alpha particle scattering and Rutherford's nuclear model of atom. At the suggestions of Ernest Rutherford in 1911, H. Rieger and E. Marsden performed some experiments. In one of their experiments as shown in figure 12.1, here is the figure 12.1, they directed a beam of 5.5 MeV alpha particles emitted from a 83-214 bismuth radioactive source at a thin metal foil made of gold. Figure 12.2 shows a schematic diagram of this experiment. Alpha particles emitted by a 83-214 bismuth radioactive source were collimated into a narrow beam by their passage through lead bricks. The beam was allowed to fall on a thin foil of gold of thickness 2.1 into 10 to the power minus 7 meter. The scattered alpha particles were observed through a rotatable detector consisting of zinc sulfide screen and a microscope. The scattered alpha particles on striking the screen produced brief light flashes or scintillations. These flashes may be viewed through a microscope, and the distribution of the number of scattered particles may be studied as function of angle of scattering. Here you can see 12.2 diagram, schematic arrangement of Geiger-Marsden experiment. A typical graph of the total number of alpha particles scattered at different angles in a given interval of time is shown in figure 12.3. The dots in this figure represent the data points, and the solid curve is the theoretical prediction based on the assumption that the target atom has a small, dense, positively charged nucleus. Many of the alpha particles pass through the foil. It means that they do not suffer any collisions. Only about 0.14% of the incident alpha particles scatter by more than 1 degree, and about 1 in 8,000 deflected by more than 90 degree. Rutherford argued that to deflect the alpha particle backwards, it must experience a large repulsive force. This force could be provided if the greater part of the mass of the atom and its positive charge were concentrated tightly at its center. Then the incoming alpha particle could get very close to the positive charge without penetrating it, and such a close encounter would result in a large deflection. This agreement supported the hypothesis of the nuclear atom. This is why Rutherford is credited with the discovery of the nucleus. In Rutherford's nuclear model of the atom, the entire positive charge and most of the mass of the atom are concentrated in the nucleus, with the electrons some distance away. The electrons would be moving in orbits about the nucleus just as the planets do around the sun. Rutherford's experiments suggested the size of the nucleus to be about 10 to the power minus 15 meter to 10 to the power minus 14 meter. From kinetic theory, the size of an atom was known to be 10 to the power minus 10 meter, about 10,000 to 100,000 times larger than the size of the nucleus. Thus, the electrons would seem to be at a distance from the nucleus of about 10,000 to 100,000 times the size of the nucleus itself. Thus, most of an atom is empty space. With the atom being largely empty space, it is easy to see why most alpha particles go right through a thin metal foil. However, when alpha particle happens to come near a nucleus, the intense electric field there is scattered it's through a large angle. The atomic electrons, being so light, do not appreciably affect the alpha particles. The scattering data shown in figure 12.3 can be analyzed by employing Rutherford's nuclear model of the atom. As the gold foil is very thin, it can be assumed that alpha particles will suffer not more than one scattering during their passage through it. Therefore, computation of the trajectory of an alpha particle scattered by a single nucleus is enough. Alpha particles are nuclei of helium atoms and therefore carry 2 units. 2 electrons of positive charge and have the mass of the helium atom. The charge of the gold nucleus is Ze, where Z is the atomic number of the atom. For gold, Z is 79. Since the nucleus of gold is about 50 times heavier than an alpha particle, it is reasonable to assume that it remains stationary throughout the scattering process. Under these assumptions, the trajectory of an alpha particle can be computed employing Newton's second law of motion and the Coulomb's law for electrostatic force of repulsion between the alpha particle and the positively charged nucleus. The magnitude of this force is, here you can see the formula, where r is the distance between the alpha particle and nucleus. The force is directed along the line joining the alpha particle and the nucleus. The magnitude and direction of the force on an alpha particle continuously changes as it approaches the nucleus and recedes away from it. 12.2.1 Alpha particle trajectory. The trajectory traced by an alpha particle depends on the impact parameter B of collision. The impact parameter is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. Figure 12.4. So here is the diagram. Where I was, yes. A given beam of alpha particles has a distribution of impact parameters B, so that the beam is scattered in various directions with different probabilities. In a beam, all particles have nearly same kinetic energy. It is seen that an alpha particle close to the nucleus, the small impact parameter, suffers large scattering. In case of head-on collision, the impact parameter is minimum and the alpha particle rebounds back theta is approximately 2 pi. For a large impact parameter, the alpha particle goes nearly undeviated and has a small deflection. Theta is approximately equals to 0. The fact that only a small fraction of the number of incident particles rebound back indicates that the number of the number of alpha particles undergoing head-on collision is small. This in turn implies that the mass of the atom is concentrated in a small volume. Rutherford scattering therefore is a powerful way to determine an upper limit into the size of the nucleus. So now here you can see the first example, 12.1, that you have to read by yourself. Example 2. Now 12.2.2 electron orbits. The Rutherford nuclear model of the atom, which involves classical concepts, pictures the atom as an electrically neutral sphere consisting of very small, massive and positively charged nucleus at the center surrounded by the revolving electrons in their respective dynamically stable orbits. The electrostatic force of attraction Fe between the revolving electrons and the nucleus provides the requisite centripetal force Fc to keep them in their orbits. Thus, for a dynamically stable orbit in a hydrogen atom, Fe is equals to Fc. So here is the formula. Next, thus the relation between the orbit radius and the electron velocity is here. You can see the kinetic energy K and electrostatic potential energy of the electron in hydrogen atom are, you can see here. The negative sign in U signifies that the electrostatic force is in the minus R direction. Thus the total energy E of the electron in a hydrogen atom is, you can see here. The total energy of the electron is negative. This implies the fact that the electron is bound to the nucleus. If E were positive, an electron will not follow a closed orbit around the nucleus. Example 12.3 you can see here. Now 12.3 atomic spectra. As mentioned in 12.1 section, each element has a characteristic spectrum of radiation which it emits. When an atomic gas or vapor is excited at low pressure, usually by passing an electric current through it, the emitted radiation has a spectrum which contains certain specific wavelengths only. A spectrum of this kind is termed as emission line spectrum, and it consists of bright lines on a dark background. The spectrum emitted by atomic hydrogen is shown in figure 12.5. Study of emission line spectra of material can therefore serve as a type of fingerprint for identification of the gas. When white light passes through a gas, we analyze the transmitted light using a spectrometer. We find some dark lines in the spectrum. These dark lines correspond precisely to those wavelengths which were found in the emission line spectrum of the gas. This is called the absorption spectrum of the material of the gas. Here you can see 12.5 diagram. Emission lines in the spectrum of hydrogen. 12.3.1 spectral series. We might expect that the frequencies of the light emitted by a particular element would exhibit some regular pattern. Hydrogen is the simplest atom and therefore has the simplest spectrum in the observed spectrum. However, at first sight, there does not seem to be any resemblance of order or regularity in spectral lines. But the spacing between lines within certain sets of hydrogen spectrum decreases in a regular way. Figure 12.5 you have already seen. Each of these sets is called a spectral series. In 1885, the first such series was observed by a Swedish school teacher, Johann Jacob Balmer, 1825 to 1898, in the visible region of the hydrogen spectrum. This series is called Balmer series. The line with the longest wavelength 656.3 nm in the red is called H alpha. The next line with wavelength 486.1 nm in the blue-green is called H beta. The third line 434.1 nm in the violet is called H gamma, and so on. As the wavelength decreases, the line appears closer together and are weaker in intensity. Balmer found a simple empirical formula for the observed wavelengths. Here you can see the formula. Where lambda is the wavelength, r is a constant called the Rydberg's constant, and n may have integral values 3, 4, 5, etc. The value of r is 1.097 into 10 to the power 7 per meter. This equation is called Balmer formula, and here they are taking the n is equals to 3 in equation and they are obtaining this. Now they are putting the value n is equals to 4 and one obtains a wavelength of H beta line, etc. for n is equals to infinity. One obtains the limit of the series at lambda is equals to 364.6 nm. This is the shortest wavelength in the Balmer series. Beyond this limit, no further distinct lines appear. Instead, only a faint continuous spectrum is seen. Other series of spectra for hydrogen were subsequently discovered. These are known after their discoveries as Lyman, Paschen, Brackett and Pfund series. These are represented by the formula. Here you can see all the formulas. Lyman, Paschen, Brackett and Pfund series. The Lyman series is in the ultraviolet and the Paschen and Brackett series are in the infrared region. The Balmer formula equation 12.5 may be written in the terms of frequency of the light, recalling that. Here you can see there are only a few elements, hydrogen, singly ionized helium and doubly ionized lithium, whose spectra can be represented by simple formula like equations 12.5 to 12.9. These equations are useful as they give the wavelengths that hydrogen atoms radiate or absorb. However, these results are empirical and do not give any reasoning why only certain frequencies are observed in the hydrogen spectrum. 12.4 Bohr model of the hydrogen atom. The model of the atom proposed by Rutherford assumed that the atom consisting of a central nucleus and revolving electron is stable, much like sun-planet system which the model imitates. However, there are some fundamental differences between the two situations. While the planetary system is held by gravitational force, the nucleus electron system being charged objects interact by Coulomb's law of force. We know that an object which moves in a circle is being constantly accelerated, the acceleration being centripetal in nature. According to classical electromagnetic theory, an accelerating charged particle emits radiation in the form of electromagnetic waves. The energy of an accelerating electron should therefore continuously decreases. The electron would spiral inward and eventually fall into the nucleus. Figure 12.7. Thus, such an atom cannot be stable. Further, according to the classical electromagnetic theory, the frequency of the electromagnetic waves emitted by the revolving electrons is equal to the frequency of revolution. As electrons spiral inwards, their angular velocities and hence their frequencies would change continuously, and so will the frequency of the light emitted. Thus, they would emit a continuous spectrum, in contradiction to the line spectrum actually observed. Clearly, Rutherford model tells only a part of the story, implying that the classical ideas are not sufficient to explain the atomic structure. See this diagram. Now, Niels Henrik David Bohr, 1885 to 1962, Danish physicist who explained the spectrum of hydrogen atom based on quantum ideas, and he gave a theory of nuclear fission based on liquid drop model of nucleus. Bohr contributed to the clarification of the conceptual problems in quantum mechanics, in particular by proposing the complementary principle. Example 12.4. It was Niels Bohr, 1885 to 1962, who made certain modifications in this model by adding the ideas of the newly developing quantum hypothesis. Bohr studied in Rutherford's laboratory for several months in 1912, and he was convinced about the validity of Rutherford's nuclear model. Faced with the dilemma as discussed above, Bohr in 1930 concluded that in spite of the success of electromagnetic theory in explaining large-scale phenomena, it could not be applied to the process at the atomic scale. It became clear that a fairly radical departure from the established principles of classical mechanics and electromagnetism would be needed to understand the structure of atoms and the relation of atomic structure of two atomic spectra. Bohr combined classical and early quantum concepts and gave his theory in the form of three postulates. These are: number 1. Bohr's first postulate was that an electron in an atom could revolve in certain stable orbits without the emission of radiant energy, contrary to the prediction of electromagnetic theory. According to this postulates, each atom has certain definite stable states in which it can exist, and each possible state has definite total energy. These are called the stationary states of the atom. Number 2. Bohr's second postulate defines these as stable orbits. This postulate states that the electron revolves around the nucleus only in those orbits for which the angular momentum is some integral multiple of h upon 2 pi, where h is a Planck constant, value is 6.6 into 10 to the power minus 34 joule second. Thus, the angular momentum L of the orbiting electron is quantized. that is L is equals to NH upon 2 pi. Third, Bohr's third postulates incorporated into atomic theory the early quantum concepts that had been developed by Planck and Einstein. It states that an electron might make a transition from one of its specified non-radiating orbits to another of lower energy. When it does so, a photon is emitted having energy equal to the energy difference between the initial and the final states. The frequency of the emitted photon is then given by h nu is equals to E I minus EF, and where EI and EF are the energies of the initial and the final states, and E initial is greater than E final. For a hydrogen atom, equation 12.4 gives the expression to determine the energies of different energy states. But then this equation requires the radius r of the electron orbit. To calculate r, Bohr's second postulate about the angular momentum of the electron, the quantization condition is used. The angular momentum L is given by L is equals to mvr. And here you can see Bohr's second postulate of quantization says that the allowed values of angular momentum are integral multiples of h upon 2 pi. Ln is equals to mvn, Rn is equals to nh upon 2 pi, nh upon 2. Where n is an integer, Rn is the radius of nth possible orbit, and Vn is the speed of moving electron in the nth orbit. The allowed orbits are numbered 1, 2, 3 according to the values of n, which is called the principal quantum number of the orbit. Here you can see the complete calculation. All reactions. The negative sign of the total energy of an electron moving in an orbit means that the electron is bound with the nucleus. Energy will thus be required to remove the electron from the hydrogen atom to a distance infinitely far away from its nucleus or proton in hydrogen atom. The derivation of equations involves the assumption that electronic orbits are circular, though orbits under inverse square force are in general elliptical. Planets move in elliptical orbits under the inverse square gravitational force of the Sun. However, it was shown by the German physicist Arnold Sommerfeld 1868 to 1951 that when the restriction of circular orbit is relaxed, these equations continue to hold even for elliptic orbits. Orbit versus state, orbital picture of electron in atom. We are introduced to the Bohr model of atom one time or the other in the course of physics. This model has its place in the history of quantum mechanics and particularly in explaining the structure of an atom. It has become a milestone since Bohr introduced the revolutionary idea of definite energy orbits for the electrons, contrary to the classical picture requiring an accelerating particles to radiate. Bohr also introduced the idea of quantization of angular momentum of electrons moving in definite orbits. Thus, it was a semi-classical picture of the structure of atom. Now, with the development of quantum mechanics, we have a better understanding of the structure of atom. Solutions of the Schrödinger wave equation assign a wave-like description to the electrons bound in an atom due to attractive forces of its protons. An orbit of the electrons in the Bohr model is the circular path of motion of an electron around the nucleus. But according to the quantum mechanics, we cannot associate a definite path with the motion of the electrons in an atom. We can only talk about the probability of finding an electron in a certain region of space around the nucleus. This probability can be inferred from the one electron wave function called the orbital. This function depends only on the coordinates of the electron. It is therefore essential that we understand the subtle differences that exist in two models. Bohr model is valid for only one electron atoms, ions or energy value assigned to each orbit. Depends on the principal quantum number n in this model. We know that energy associated with a stationary state of an electron depends on n only for one electron atoms or ions. For a multi-electron atom or ion, this is not true. The solution of the Schrödinger wave equation obtained for hydrogen-like atoms, ions, called the wave function, gives information about the probability of finding an electron in various regions around the nucleus. This orbital has no resemblance whatsoever with the orbit defined for an electron in the Bohr model. Here is the example 12.5. 12.4.1 Energy levels. The energy of an atom is the least largest negative value when its electron is revolving in an orbit closest to the nucleus, that is the one for which n is equals to 1. For n 2, 3 and so on, the absolute value of the energy is smaller. Hence the energy is progressively larger in the outer orbits. The lowest state of the atom, called the ground state, is that of the lowest energy, with the electron revolving in the orbit of the smallest radius, the Bohr radius A0. The energy of this state n is equals to 1, E1 is equals to minus 13.6 electron volt. Therefore, the minimum energy required to free the electron from the ground state of the hydrogen atom is 13.6 eV. It is called ionization energy of the hydrogen atom. This prediction of Bohr's model is an excellent agreement with the experimental value of ionization energy. At room temperature, most of the hydrogen atoms are in ground state. When a hydrogen atom receives energy by processes such as electron collisions, the atom may acquire sufficient energy to raise the electron to higher energy states. The atom is then said to be in an excited state. From equation 12.19 for n is equals to 2, the energy E2 is minus 3.40 electron volt. It means that the energy required to excite an electron in hydrogen atom to its first excited state is an energy equal to E2 minus E1. So here you can find the value. Or to excite the hydrogen atom from its ground state to second excited state, 12.09 electron volt energy is required, and so on. From these excited states, the electrons can then fall back to state of lower energy, emitting a photon in the process. Thus, as the excitation of hydrogen atom increases, that is, as n increases, the value of minimum energy required to free the electron from the excited atom decreases. The energy level diagram for the stationary states of a hydrogen atom computed from equation 12.19 is given in figure 12.8. The principal quantum number n labels the stationary states in the ascending order of energy. In this diagram, the highest energy state corresponds to n is equals to infinity in equation 12.19 and has an energy of 0 electron volt. This is the energy of the atom when the electron is completely removed, R is equals to infinity, from the nucleus and it is at rest. Observe how the energies of the excited states come closer and closer together as an increase. Frank-Hertz experiment. The Frank-Hertz experiment है. The existence of discrete energy levels in an atom was directly verified in 1914 by James Frank and Hertz. They studied the spectrum of mercury vapor when electrons having different kinetic energies passed through the vapor. The electron energy was varied by subjecting the electrons to electric field by varying strength. The electrons collide with the mercury atoms and can transfer energy to the mercury atoms. This can only happen when the energy of electron is higher than the energy difference between an energy level of Hg occupied by an electron and a higher unoccupied level. You can see the diagram. For instance, the difference between an occupied energy level of Hg and a higher unoccupied level is 4.9 electron volt. If an electron of having an energy of 4.9 electron volt or more passes through mercury, an electron in mercury atom can absorb energy from the bombarding electron and get excited to the higher level. The colliding electron's kinetic energy would reduce by this amount. You can see the diagram A. The excited electron would subsequently fall back to the ground state by emission of radiation, figure B. The wavelength of emitted radiation you can see here. The value is 253 nm. By direct measurement, Frank and Hertz found that the emission spectrum of mercury has a line corresponding to this wavelength. For this experimental verification of Bohr's basic ideas of discrete energy levels in atoms and the process of photon emission, Frank and Hertz were awarded the Nobel Prize in 1925. 12.5. The line spectra of the hydrogen atom. According to the third postulates of Bohr's model, when an atom makes a transition from the higher energy state with quantum number Ni to the lower energy state, the quantum number Nf, the difference of energy is carried away by a photon of frequency VIF such that you can see the complete equations here. This is a value very close to the value 1.097 into 10 to the power 7 per meter obtained from the empirical Bohr formula. This agreement between the theoretical and experimental values of the Rydberg constant provided a direct, striking confirmation of the Bohr's model. Since both NF and NI, that is N final and N initials, are integers, these immediately shows that in transitions between different atomic levels, light is radiated in various discrete frequencies. For hydrogen spectrum, the Babel formula corresponds to NF is equals to 2 and Ni is equals to 3, 4, 5, etc. The results of the Bohr's model suggested the presence of other series spectra for hydrogen atom, those corresponding to the transitions resulting from NF is equals to 1 and Ni is equals to 2, 3, etc. NF is equals to 3 and Ni is equals to 4, 5, etc. and so on. Such series was identified in the course of spectroscopic investigations and are known as the Lyman-Balmer, Paschen bracket and Pfund series. The electronic transition corresponding to these series are shown in figure 12.9. This is figure 12.9. The various lines in the atomic spectra are produced when electrons jump from higher energy state to a lower energy state and photons are emitted. These spectral lines are called emission lines. But when an atom absorbs a photon that has precisely the same energy needed by the electron in a lower energy state to make transitions to a higher energy state, the process is called absorption. Thus, if photons with a continuous range of frequencies pass through a rarefied gas and then are analyzed with a spectrometer, a series of dark spectral absorption lines appear in the continuous spectrum. The dark lines indicates the frequencies that have been absorbed by the atoms of the gas. The explanation of the hydrogen atom spectrum provided by Bohr's model was a brilliant achievement which greatly stimulated progress towards the modern quantum theory in 1922. Bohr was awarded Nobel Prize in Physics. Here you can see the next example, 12.6. 12.6 de Broglie's explanation of Bohr's second postulate of quantization. Of all the postulates Bohr made in this model of the atom, perhaps the most puzzling in his second postulate. It states that angular momentum of the electron orbiting around the nucleus is quantized, that is ln is equals to nh upon 2 pi, where n is equals to 1, 2, 3 and so on. Why should the angular momentum have only those values that are integral multiples of h upon 2 pi? The French physicist Louis de Broglie explained this puzzle in 1923, 10 years after Bohr proposed his model. We studied in chapter 11 about the de Broglie's hypothesis that material particles such as electrons also have a wave nature. C.J. Davison and L.S. Germer later experimentally verified the wave nature of electrons in 1927. Louis de Broglie argued that the electron in its circular orbit as proposed by Bohr must be seen as a particle wave. In analogy to wave traveling on a string, particles waves too can lead to standing waves under resonant condition. From chapter 15 of class 11 physics textbook, we know that when a string is plucked, a vast number of wavelengths are excited. However, only those wavelengths survive which have nodes at the ends and form the standing wave in the string. It means that in a string, standing waves are formed when the total distance traveled by a wave down the string and back is 1 wavelength, 2 wavelength or any integral number of wavelengths. Waves with other wavelengths interfere with themselves upon reflection and their amplitudes quickly drop to 0. For an electron moving in nth circular orbit, radius Rn, the total distance is the circumference of the orbit, 2 pi Rn thus. So the value of 2 pi Rn is equals to n lambda, where n is equals to 1, 2, 3 and so on. Figure 12.10 illustrates a standing particle wave on circular orbit for n is equals to 4, that is 2 pi Rn is equals to 4 lambda, where lambda is the de Broglie's wavelength of the electron moving in nth orbit. From chapter 11 we have lambda is equals to h upon p, where p is the magnitude of the electron's momentum. If the speed of the electron is much less than the speed of light, the momentum is mvn. Thus lambda is equals to h upon mvn. From equation we have 2 pi Rn is equals to nh upon mvn, or mvn Rn is equals to nh upon 2 pi. This is the quantum condition proposed by Bohr for the angular momentum of the electron. In section 12.5 we saw that this equation on the basis of explaining the discrete orbits and energy level in hydrogen atom. Thus, de Broglie hypothesis provided an explanation for Bohr's second postulate for the quantization of angular momentum of the orbiting electron. The quantized electron orbits and energy states are due to the wave nature of the electron, and only resonant standing waves can persist. Bohr's model involving classical trajectory picture planet-like electron orbiting the nucleus correctly predicts the gross feature of the hydrogenic atoms. In particular, the frequencies of the radiation emitted or selectively absorbed. The model, however, has many limitations. Some are: number one, the Bohr model is applicable in hydrogenic atoms. It cannot be extended even to mere 2 electron atoms such as helium. The analysis of atoms with more than one electron was attempted on the lines of Bohr's model for hydrogenic atoms but did not meet with any success. Difficulty lies in the fact that each electron interacts not only with the positively charged nucleus but also with all other electrons. The formulation of Bohr model involves electrical force between positively charged nucleus and electron. It does not include the electrical forces between electrons which necessarily appear in multi-electron atoms. Number 2. While the Bohr's model correctly predicts the frequencies of the light emitted by hydrogenic atoms, the model is unable to explain the relative intensities of the frequencies in the spectrum. In emission spectrum of hydrogen, some of the visible frequencies have weak intensity, others strong. Why? Experimental observation depict that some transitions are more favored than Bohr's. Bohr's model is unable to account for the intensity variation. Bohr's model presents an elegant picture of an atom and cannot be generalized to complex atoms. For example, atoms we have to use a new and radical theory based on quantum mechanics, which provides a more complete picture of the atomic structure. Laser light. Imagine a crowded marketplace in a railway platform with people entering a gate and going towards all directions. Their footsteps are random and there is no phase correlation between them. On the other hand, think of large number of soldiers in a regulated march. Their footsteps are very correlated. See figure here. This is similar to the difference between light emitted by an ordinary source like a candle or a bulb and that emitted by a laser. The acronym LASER stands for Light Amplification by Stimulated Emission of Radiation. Since its development in 1960, it has entered into all areas of science and technology. It has found applications in physics, chemistry, biology, medicine, surgery, engineering, etc. There are low power lasers with a power of 0.5 called pencil lasers, which serve as pointers. There are also lasers of different powers suitable for delicate surgery of eye or glands in the stomach. Finally, there are lasers which can cut or weld steels. Light is emitted from a source in the form of packets of the waves. Light coming out from an ordinary source contains a mixture of many wavelengths. Light coming out from an ordinary source contains a mixture of many wavelengths. There is also no phase relation between the various waves. Therefore, such light, even if it is passed through an aperture, spreads very fast and the beam size increases rapidly with distance. In case the lace of laser light, the wavelength of each packet is almost the same. Also, the average length of the packets of waves is much larger. This means that there is a better phase correlation over a longer duration of time. This results in reducing the divergence of a laser beam substantially. If there are n atoms in a source, each emitting light with intensity I, then the total intensity produced by an ordinary source is proportional to Ni, whereas in a laser source, it is proportional to N square I. Considering that N is very large, we see that the light from a laser can be much stronger than that from an ordinary source. When astronauts of the Apollo mission visited the moon, they placed a mirror on its surface facing the Earth. The scientists on the Earth sent a strong laser beam which was reflected by the mirror on the moon and received back on the Earth. The size of the reflected laser beam and the time taken for the round trip were measured. This allowed a very accurate determination of extremely small divergence of laser beam and b, the distance of the moon from the Earth. Summary. Atom as a whole is electrically neutral and therefore contains equal amount of positive and negative charges. Number 2, in Thomson's model, an atom is a spherical cloud of positive charges with electrons embedded in it. Third, in Rutherford's model, most of the mass of the atom and all its positive charge are concentrated in a tiny nucleus, typically 1 by 10,000, the size of an atom, and the electrons revolve around it. Fourth, Rutherford nuclear model has two main difficulties in explaining the structure of atom. A. It predicts that atoms are unstable because the accelerated electrons revolving around the nucleus must spiral into the nucleus. This contradicts the stability of matter. B. It cannot explain the characteristic line spectra of atoms of different elements. Fifth, atoms of each element are stable and emit characteristic spectrum. The spectrum consists of a set of isolated parallel lines termed as line. The spectrum, it provides useful information about the atomic structure. Sixth, the atomic hydrogen emits a line spectrum consisting of various series. The frequency of any line in a series can be expressed as a different of two terms. Here you can see Lyman, Balmer, Paschen, bracket, Fun. All series are here. Seventh, to explain the line spectra emitted by atoms as well as the stability of atom, Niels Bohr proposed a model for hydrogenic single electron atoms. Niels Bohr proposed a model for hydrogenic single electron atom. He introduced three postulates and laid the foundations of quantum mechanics. A. In a hydrogen atom, an electron revolves in certain stable orbits called a stationary orbit without the emission of radiant energy. B. The stationary orbits are those for which the angular momentum is some integral multiple of h upon 2 pi. C. The third postulate states that an electron might make a transition from one of its specified non-radiating orbits to another of lower energy. When it does so, a photon is emitted having energy equal to the average difference between the initial and final states. Here you can see the equations. Eighth point is, as a result of the quantization condition of angular momentum, the electron orbits of the nucleus at only specific radii. For a hydrogen atom, it is given by this equation. Here is another formula of energy. Ninth, de Broglie's hypothesis that electrons have a wavelength lambda is equals to h upon mv gave an explanation for Bohr's quantized orbits by bringing in the wave-particle duality. The orbits corresponds to circular standing waves in which the circumference of the orbit equals a whole number of wavelengths. 10th, Bohr's model is applicable only to hydrogenic atoms. It cannot be extended to even two electron atoms such as helium. This model is unable to explain for the relative intensities of the frequencies emitted even by hydrogenic atom. So इसी के साथ ही आपका चैप्टर कंप्लीट हो गया. अगर इस ऑडियो बुक ने आपकी हेल्प की हो तो इसे लाइक ज़रूर करना, चैनल को सब्सक्राइब कीजिएगा एंड अपने दोस्तों के साथ में ज़रूर शेयर कीजिएगा. और नेक्स्ट किस चैप्टर की ऑडियो बुक आपको चाहिए मुझे कमेंट सेक्शन में ज़रूर बताइएगा. तो सी यू सून इन द नेक्स्ट वीडियो. टिल देन जस्ट स्टे ट्यून्ड विद मी. बाय बाय.